Free energy is defined as the amount of energy available to do work. Or another way to look at this is it is the amount of energy that is available for release in a chemical reaction. So this really is kind of a type of potential energy. We do designate it with a capital G, and that's named after the individual that first defined this. So his last name was Gibbs, so that's where the G comes from. But if we think first about a chemical reaction, we are going to start with reactants. And those reactants throughout the course of the reaction are going to get converted into products. So the reactant will have a certain amount of free energy, or G, and the products will have a certain amount of free energy, or G. And what we're really going to be interested in here is the difference between the two. And we define this as delta G. And the little delta symbol, that does mean change. So what we're saying here is we're interested in how the amount of free energy changes from the beginning of the reaction till the end of the reaction. And so if we did want to actually put an equation here, we define this as the amount of free energy of the products subtracting off the amount of free energy of the reactants. And so depending on the actual amount of energy that we had, we could come up with a positive or a negative number when we calculate the delta G, or the change in free energy. So this brings us to two major categories of reactions, or classes of reactions, and it does have to do with the sign, so positive or negative, of that free energy amount. So this concept is going to bring us to two different types of reactions. The big difference between these two types will be the value, or really more specifically, the sign of that delta G number. So with exergonic reactions, if we look at that one first, exergonic means energy outward. And so exer is out, and so it's out and it's energy. And that is what's going to happen in this one. So if we look at that, in this case, we're going to start with a reactant that has a whole lot of energy. So I'm going to draw this kind of like a little bar graph here. So I've got a big bar for my reactant, but then when we get to the product only has a little bit of energy. So if you look at this, okay, so this is my graph showing free energy. So I'm going to put G over here on this side. The reactant has a bunch, the product doesn't have much. Well, if we remember the laws of thermodynamics, we know that energy can't disappear. So this big difference between the two, the energy that has gone away, so to speak, that value right there, that's the delta G. And so it's the change, the difference in the amount of energy between the reactants and the products. But if we plug the numbers into the equation that we looked at before, we would have just, remember, it's the amount of energy in the products minus the amount of energy in the reactants. And if you actually had values there, our delta G value is going to come out to an overall negative. So when we talk about exergonic reactions, they are energy outward reactions because that amount of energy that's no longer present in the product, that is actually going to be released. So we do have energy, and it is the difference in energy here that is actually released during the course of this reaction. So exergonic reactions, if we just added a few more details here, they are energy outward. They will always have a negative delta G. And these are also going to be what we would call spontaneous reactions. And they are spontaneous, meaning that these are reactions that are going to occur without any kind of input in energy. So this is the natural tendency, so to speak. So these will be, again, spontaneous, but I will emphasize that spontaneous does not necessarily mean that these are going to be fast reactions, but they're reactions that don't require energy to be input. If we're talking about the other type down here, endergonic is like inside energy, or I'm going to just write it here, energy inward. And so they are going to be essentially the opposite of the exergonic reactions. So if we were to draw our same diagram here, and I've got energy on the side, and I were to put a bar for my reactant this time is going to have a small amount of energy, and my product is going to get much more. So if I end up with this product that has a lot more energy than the reactant, it's a big energy difference. And that energy did have to come from somewhere. So this energy difference that we're now seeing here is still the delta G, but this is energy that actually came in. So by energy that came in, that means that this reaction requires an input in energy. And if you were to take the same equation we used before and plug values in for the reactants and the products and their amount of free energy, we would have a delta G that's going to be positive. So these endergonic reactions always have a positive delta G, and they are not going to be spontaneous. And the reason they are not spontaneous is because they require energy. So these reactions will not happen if there is not some input of energy available to really force them along. So this is similar to the ball. If we look at this first one, okay, so here's my hill. If I had a ball on the top of the hill, we really don't have to do anything to get this ball to roll down the hill. May take a little nudge, but essentially that ball is going to roll right down the hill. So that's spontaneous. This reaction on the bottom, if we were to draw our same hill, but now we put the ball down here on the side, to get that ball up to the top of the hill is going to require effort. So you would actually have to push that ball up the hill to really get it up there. So again, exergonic is like we're rolling down the hill. It's going to be spontaneous. Energy is coming out. And if we're using our ball example, that could be in the form of kinetic energy. And then the endergonic reaction is energy inward. We're going to have to force this reaction to take place. So we're going to push the ball up the hill, or another way to look at it is that we're going to take a ball that was very stable or a molecule that's very stable, and we're going to turn it into a much more unstable state. And the more unstable something is, the more energy that it actually has.